then we can begin this seminar. So welcome everyone and good morning. And welcome to this seminar about automatic kitting. The title here is in Swedish, but the title basically translates to automatic kitting in English. So my name is Patrik Fager. I work as a researcher at Scilab at the division of production systems at industrial and material science at Chalmers. And my research area is logistics, and at Scilab we look at different ways of utilizing Industry 4.0 to support materials handling activities in production settings, basically. Today, I'm going to present a project that we have been working on for quite some time now, where we have built an automatic process for kit preparation. And for those of you who are here and listening, I'm going to present a lot of technical details about this setup today. The logistics perspective is something we are working towards, and it's the end goal of this setup, to be able to study different logistics questions related to automatic kitting. But so far this project has been a lot about developing the technology and making the process actually work. So it is that perspective, the technical perspective, I will present today. I can also mention that with my background, I'm a mechanical engineer and a logistics researcher. So this with IT systems and engineering of IT systems is not my specialty. I'm not trained in this, but we have gotten a lot of support from very knowledgeable people about how to build this process. So hopefully we have followed good standards when we have built this process. And finally, we have gotten quite good support from the various companies that have been supplying the technology here. So Solomon and Yaskava, and also Siemens, which I will come to later. And with that said, I would like to start with just introducing the topic of kitting or kit preparation. So this is a type of process that is very common in assembly systems, in the materials flow up to the assembly line. And you need to perform kit preparation when you use a kitting material supply, which basically means that components are arranged in one package before they are delivered to the assembly, so that the components for one assembly object is available at the assembly process. And kitting is a good method to use when you have a lot of different component variants in order to better and more effectively manage the material flow. So kit preparation is the base context of the setup I'm going to present today. And at Scilab, we are working with building a factory, a simulated production of drones, which are these small helicopter-like devices. So at Scilab, we are building basically a supply chain for manufacturing these drones. And as you see on the flow, on the left picture here, we have some subcontractors, which is partly additive manufacturing and partly just raw procurement. So we have some components for the drone which we 3D print and so on. Then we have an in-house logistics area where we handle the components, and this is where the kitting area is. We have a final assembly, a quality assurance, and also delivery of the drones. And this is an ongoing project, so it's not finished yet. But today I'm going to present a part of this production flow. And as an overview of the different components of the automated kitting process, I created this view here. And as you see on the left, we have a vision system and a robot which communicates with a PC. And the PC in turn is connected to a router, which is connected to a Raspberry Pi containing an OPC UA server. This OPC UA server is read by a gateway, which sends the data to mines where we can visualize the robot status and see how well the process performs in real time, basically. So this is what I'm going to present today. I'm going to present all these different parts and explain how we have configured them. For those of you who are listening, in real time now and not for the YouTube presentation, if you have any ideas or suggestions on different ways we can achieve this, alternatives and so on, then please leave comments here in the chat. And I guess also for the YouTube video, you can leave comments in the chat there as well. So the agenda I have set up looks like this. We have a first part where I will describe the robot which we have used and how that is configured. Then I will talk some about the vision system we are using and the different parts there and how we have set it up. Then I will say a few words about order management, how we can send instructions to the robot to prepare a kit. Then I will explain this visualization interface and interoperability. By that I mean how we have connected all these different parts through a homemade middleware, you can call it. After that, I will show the setup in action, a video recording of when the robot prepares a kit. And at last, I will say a few words about the further work we have to do with this process and our ideas for the future. Any questions that you have, you can either write them in the chat or we can discuss them after the presentation is over. I think I will talk for about 30 to 40 minutes. There are a lot of pictures, so it might go quicker than that, but we will see. So for the first part, the robot, we are using a Yaskawa HC10. It's a 6-axis robot arm with a payload capacity of 10 kilograms. We have it mounted on a 7th axis, so it can access different shelves at the kitting area. And we control it as a 7th axis. So every position we send to the robot, we have to define 7 different joint values, basically. And the complete setup, as you see in the right picture there, we also have a scanner mounted above a rack, which is linked to the robot via PC. So a bit more specific about the robot, we're using a YRC1000 controller, which is connected to a pendant where we can perform manual teaching of the robot. But we have also developed an interface for remote PC control of the robot, which I will talk about during this presentation. We have different types of fingers for the robot, and we have the ability to print new fingers here at the lab. The gripper, as you see in the 3rd picture there, is from Schunk. It's a coax gripper, and we can, as you see on the bottom there, attach the different fingers to this gripper module. We have a homemade housing, also 3D printed, to package together the different wires and connections for the gripper module. And I should say as well that the Yaskawa HC10 is prepared for collaborative applications. So it has 4 sensors and the ability to enter collaborative mode. And for the video recording I will show later, we are using it in collaborative mode, which basically means that it moves slower and it's more sensitive to impacts so that it stops. And that means also that we don't have to put the robot in a cage. We can have it uncaged and people nearby, basically. So for the robot control, we have developed an interface, or not developed, we have made use of an interface that's available on the YRC 1000 controller. And this interface is called high-speed Ethernet, and there is a manual for how this can be implemented, which is available online. The interface makes use of a UDP protocol, so it's unidirectional. So we send a message, but we are not sure that we get a response, so to say. So we have to listen to the socket after we have sent the message. The benefit of this protocol is that it's very fast. We get a response in less than 0.1 seconds, but usually it's a lot less for the smaller commands. So it's a very quick protocol. But this is built into the YRC 1000. So this is not something we have designed, but rather made use of, so to say. But we have had to write the driver for our on our own. There are some examples available online, but most of the code we have had to develop from scratch, so to say. But the interface has support for different functions of controlling the robot. We can monitor the robot status. We can perform file control, loading files, reading files, select the master job, and also start different jobs. Of course, servo control we can also do, and we have support for alarm and error control. And so basically with this interface we can control the robot completely, and we can do it from a PC basically. A bit more details here about this interface. We have implemented it with a response decoder for each command, so that we can check that the robot received the command correctly. So we have a two-way communication, basically. The general command structure consists of a header, which is 24 bytes large, a subheader, which is 8 bytes large, and then we have a data part, which is variable size depending on which command we send. And an example here of how the command looks, you see at the bottom, it's usually hexadecimal numbers and characters. So it's not, it took some time before we figured out exactly how it works, but once we got down the basic syntax, it's actually a quite effective interface, so to say. So we have implemented this by building a driver, as we call it, in Python, and we have designed this driver as a class which we can reuse in different applications. And then there are quite many lines of code. It's code in this class, but benefit of having it as a class is that we can reuse it for various purposes, basically. And that's the base things about the robot. For the vision system, we are using a system from Solomon, which consists of a scanner and a software. So on the first picture here, you see different characteristics of the scanner. So it has a working distance of up to 2 meters and a smallest working distance of 450 millimeters. And as you see on the picture there, the field of view becomes greater the farther away the scanner is used. But the precision of the scanner, as you see in brackets there, at 2 meters, the precision is 1.8 millimeters, while at 450 millimeters working distance, it's 0.15 millimeters. So this is also an aspect that we have accounted for to some extent in our setup, because if we're looking at finer characteristics of the components to pick, then we have to have them closer to the scanner, so to say. But still, even at 2 meters, the precision is quite good with this system. Yeah, the system is based on structured light technology, and the scanner weighs 3 kilograms. And that's about, yeah, that's the important parts about the scanner, I would say. For the software side, because this is where the magic happens, or what you call it, with the vision technology. We have a software called AcuPick, which comes with the scanner. And in AcuPick, you can define a workflow for how the vision analysis should be performed. So you define these small blocks. It's similar to how Node-RED works. So you can trigger these different blocks by commands, basically. And a standard flow looks like this magnified picture here at the bottom half. You have a capture block for setting the scanner properties and the image properties. We have a recognition block for analyzing each picture. We have a bin config block for setting the limitations of the bin we're picking from. We have filters for selecting which components that are recognized and that we get coordinates back from the system with. And we have recorded objects where we can basically tell the system how many retries it can do before a component is marked as unpickable. And for this setup, we have defined 9 different locations. At the moment, we're only using 3 of them, but we have prepared it so that we can use all 9. And that's 1 bin and 1 part type for each of these flows, as you see here. But I will go through a bit more in detail about how each of these blocks works, because it is important to define these blocks in a good way in order for the system to work in a good way, basically. So for the first block, we have capture settings, and here we have to calibrate the scanner so that we get a good picture. We have one interface for showing the camera view, and here you can set the exposure time and the gain and gamma for the picture, which affects brightness and sharpness and so on. We have a projector setting page where the projector light or the pattern that is projected, which the system uses to create these point clouds, can be altered. And there we also have different settings that can be used. And from our experience so far, these settings are quite important in order for the system to work in a good way. But once you have these in place, you don't have to worry about them unless you change the light in the application area and so on. We also have a calibration that has to be done with the robot and the vision system for them to work well together. So this calibration is done by, as you see in the right picture here, using a chessboard and moving the chessboard around in the scanner's field of vision. So this process is actually quite simple once you have done it one time. Then you can reuse the robot script for showing this chessboard to the scanner. And it's important that this calibration becomes good because it affects the precision that the system has when the application is used, so to say. But it's once you have figured out this calibration method, then it's easy to replicate. For the second main block in the flow, we have recognition, and here there are a lot of details that has to be properly configured for the system to accurately detect components and to give good coordinates. The general workflow when you define this recognition settings you see on the left here. So first you have to select a tool, and the system has different recognition tools that can be used. We use something that's called instance segmentation, where we basically compare a reference model to the real picture and then get coordinates from that comparison. But you can also use other types of recognition tools, for example, to detect certain shape features or key points and so on. But for this application, we're using instance segmentation. Then once you have defined your tool, you have to define a region of interest within the scanner's field of view. So as you see on the top picture on the right, we have marked the bin where we want to pick components from with this certain recognizer. I can mention this as well, that for each component that you want to pick with this system, you have to perform this kind of setup. You have to define a recognizer for each component that you want to be able to pick, basically. But you define this region of interest, and then you take a lot of images, or some images at least, and then you have to annotate these images to provide training material for the model. You can also do this annotation automatically by use of a CAD model, which I will describe on the next slide. Then you have to train your model to develop kind of a reference model that the system uses to recognize the components you want to pick. And then finally, you can define a golden model, which kind of supports the training model in the detection. And the golden model is basically a good scan of the component that you want to be able to pick. For the training of the system, you can, and there is support for auto labeling, which is in contrast to manual labeling. So as you see on the top picture, the AccuPick annotations, if you're doing it manually, then you have to sit and mark the shape of each component that is that the system should see as pickable, basically. And you have to do this for about 200 to 250 instances of each class that you want to be able to recognize, and a class can be a principal orientation of the component. And to do this manually takes quite some time, and it tests the patience one has. But with this auto-labeling feature, you can we can make use of CAD files and generate fake pictures, or what you call it, that is automatically annotated, and then we can import these annotations to AccuPic and perform the training on those pictures instead. And this is this has been a good support for us so far. But basically, to do auto labeling, you load CAD files into Blender, and you adjust visual settings to make it look like a picture of the real bin, so to say. You set randomization criteria for how the components should be, or the simulated components should be organized in the pictures. You set annotation parameters for how the annotations should be drawn. You generate the images, and you can convert them so that AccuPic can understand the annotations, and then you load it to AccuPic basically. And this for a typical component takes about 15 minutes, and manual labeling takes about at least 2 hours, at least from my experience. Then when you define your process, you can set up a bin config block where you define the bin that the robot should pick from. And here, once you have defined the bin, the robot knows that, or rather AccuPic doesn't give the robot coordinates that would mean that it have to move through the bin wall, for example. So by this configuration, the robot always enters the bin from the top, basically. So this is also a good support for this project. We have some filters for selecting which objects to pick. You can define different criteria for a component to be viewed as pickable. And also there are quite a few different settings here that we have not been able to test fully yet, but there are quite good support for selecting which components to pick, basically. And here are some examples of recognition results when everything has been configured and the system is tested. So you get one part in a part of the results as 2D, and I see that I have mixed the labels here, but the picture on the left is the 2D view, and the picture on the right is obviously the 3D view. But for the 2D view, you can see which objects have been detected, and for the 3D view, you get the pick points and the rotations for each of the detected objects. And as you see here, the pick point is put at a certain place on the detected component. And this you can define in your golden model of the component. So depending on how you decide to pick the component, you can adjust where the system generates the pick point. And here's another example. And these components are for the drone that we manufacture in the lab. For controlling this scanner and software, we use Ethernet TCP/IP via a protocol block, which is part of the main flow. This block has the ability for setting customizable commands and also the feedback. So we wrote a driver in Python for managing this communication. And we also made this into a class so that it's easy to reuse for different purposes, for example, data logging and so on. For order management in the process, we are using Siemens MindSphere. And here we have defined or created an API for kit order management. This API allows us to create new orders, kit orders, to update orders and to delete orders. And this is done by a orchestrator, which is kind of it could be another IIoT platform, or it could be someone controlling the main production flow, basically. The API also allows us to get orders or get kitting instructions from the kitting process, also via these HTTP endpoints. And as you see in the middle picture here, the order object, we have defined so far a few different properties of each order, an order number, the components that are included, and also an order priority. And we can track the status here as well. So we can also set different scripts for how to manage the order and how to update the different orders based on requests. And so far we have tested it by making requests from Python, but this will be further integrated with the remaining drone factory. But we will talk about this more on the next seminar. So for visualization, we have made a data logger for the robot. And here we have made use of the Yaskawa HC10 class and run it in a Python script on a server PC. We run it as a OPC UA client. And basically the script works by asking the robot for status every 2 seconds. And from that we get the robot's online status, its servo status, its operation mode, whether it's in remote, teach, or play mode, and its running status. This is then written to a OPC UA server, which we run on a Raspberry Pi. And this is in turn linked to MindSphere through a MindSphere gateway called MindConnect Nano. It's on the lower right picture there. And the Raspberry Pi and the MindConnect Nano is both connected to the same router. So it's through the router they communicate. And these data points, the status and servo status and so on, we have mapped in MindSphere to a MindSphere asset. And that allows us to visualize how the robot performs over time, basically. And at the moment we have put this GUI up on a TV by the in-house logistics area. And you see an example of how the GUI looks like on the lower right picture there. So the current status shows the current mode, the online status, and the servo status, and the running status. And anytime these values change, we either get a green check mark or a red cross, depending on the status. You can also see how it varies over time, and we will later also calculate OEE based on this, for example. You can also upload photographs if you want to make the GUI look nicer. For interoperability, to making all these different components speak in a good way, we have written a middleware also in Python. Here we make use of the Yaskava, HC10, and Solomon classes for controlling the robot and scanner, respectively. We get the parts lists and quantities from Mindsware from the API we have created there. And when the robot is run, it loops through the parts list and basically checks off any the quantities it should pick based on the order contents. We read whether a pick has been successful or a success or fail based on the gripper IO signals. So if the gripper is fully closed after picking, we know that we have missed the component. And similarly, if we have closed the gripper but it's not fully closed, then we know that we have something in the fingers. So we regard it as a success. And for the scanner robot interaction, we have set it up by making it so that the scanner basically provides object coordinates, and we write these object coordinates into a robot job file, and then we load the job file to the robot. And the robot control is based on triggering these different job files. So for each new pick, we have to get scanner coordinates, create a job file, and then trigger the job file on the robot. And an example of the job file you see on the right here. It's in-form language, so it's quite a simple syntax, really. For the process control, when we run a picking assignment or pick a component, the general job flow is that we scan the SKU location with the scanner. We wait for the scanner to complete. We get the object coordinates. We get them back as a .json object, basically. We then write the coordinates to a pre-target and a target job file. So the pre-target job file is in a straight line above the component, but some greater distance away, and then the target job file is moving in closer to the component in a straight line, and then the pick occurs. We upload the files to the robot, we start the job, and then we monitor whether the pick is a success. If it's a success, we perform a place task or a place job. But if the pick fails, we return to home. And then we retry up to 2 times by performing a new scan and try to pick another component. But if that also fails, then we mark that in the job status, and then we move on to the next component. But here, this flow is yet to be optimized, and but this is the base structure of how the flow works today. And for managing this, we have built a GUI with different buttons for triggering these different robot commands. And it's by that interface that we have performed the tests so far. So now I'm going to show a video demonstration of how the setup works. I filmed this last Friday, and as I would have expected, the robot was a bit stubborn or a bit problematic. So I had to make a few cuts here, but hopefully you will be able to see how the full process works. We have run it quite a few times, and it has worked from start to end. But for this particular clip, we have made a few clips. But I will show you a full kitting cycle, picking 3 different component types, 5 parts in total. And at first we will see the setup here. So just to demonstrate that we haven't pre-positioned the components. They are random. And we don't have that many of the drone components yet, or at least not to test with. So that's why we have quite few components in the bins. And here we put the kit pallets in place so that we can start the work cycle. So that the robot moves in to the shelf, perform a scan. And then once the coordinates is received, the robot starts the picking activity. And as you see here, we have sped up the clip a bit. But when we run the process later, we will of course increase the speed of the robot as well. You can see on the LED indicator on the robot, whether the pick is successful or not. So it's yellow when the robot moves. And then once it has gripped the component successfully, the LED turns green. And we have a lot of optimization to do with the robot's movement as well. And to make scans in parallel when the robot works. But this is a first draft of this process, and we will optimize it further along. We have also seen that you have to use a bit different strategies depending on what the component looks like. So at the moment, we have found a few ways to pick the components that we are seeing here in the clip. And now when the robot is done, it will return to the loading area. And then the finished results can look like this. Here we have not been too careful with the exact placement of the orientation of the components, but it's possible to make it look nicer as well, to have the components more precisely placed, so to say. But this is a close-up view of when the robot picks components in the bin. So here we could as well go closer to the pallet before we drop the component to make the placement a bit more precise. But yeah, that's something we will work on. And this type of component can be problematic depending on which orientation it's put in. So there is quite some work to do with figuring out good ways to prepare picking of a component to make sure that it can be picked in most of its principal orientations. So here we are picking two different variants for the leg to the drone and the drone frame. And it's the components we need for the first assembly station in the drone factory. Finally, some further work, what we will continue with here. For the robot, it's a lot of exception handling left to handle different deviations during the picking process. Right now, there are quite a few bugs, or what you call them, so that the robot stops and so on. So that, but for that, we just have to run the process more times and figure out how to handle the exceptions. We're going to look at different gripper types. Right now we have worked with fingers, but we're also going to look at how to use vacuum in this process. Automated tool changes is also something we will look at. And we have ideas for how we can achieve that, to be able to change fingers or main tool even automatically. And also how to handle empty or inner packaging. That's also something we will look at soon. For the vision system, we would like to test to use eye in hand as well, to put a scanner on the robot arm. We want to see if we can use 2D vision in some good way. It would provide a faster recognition process. We have tested a bit with unsupervised recognition, where you don't have a training model. You just use the system's inbuilt or untrained recognition method. But from what we have tested, this is a promising approach for especially simpler components. So we'll look at a bit more on that as well soon. Motion planning, we will look at, see how we can better plan the path of the robot. For order management, we will link this logistics orchestrator in Mindsphere to our production orchestrator in the lab ThingWorks, and thereby also link it to the business system, IFS, which we have here. But we will talk more about this on the next seminar on May 24. We want to have the ability to order different kit types. For example, if the assembly should be done manually or automated or collaboratively. We're going to look at order batching and how to optimize which orders are performed in what order in the kitting process. And also material replenishment, how to replenish material when a bin becomes empty, for example. For visualization, we want to calculate the OEE numbers and also different performance indicators to track the process in a good way. And also to get order status and estimated delivery times. For interoperability, we want to connect this process to an AMR system so that we can get automated transports of the kits to assembly. And we also have some ideas on a digital twin and doing some online optimization of the process. as well as to integrate the drone factory here with the other laboratories. But all of this we will discuss more on the next seminar. We also have plans for some research studies, which I won't go into detail with now, but picking of unsorted versus sorted items, matching gripper types with the component characteristics, how to allocate tasks between a human and a robot in a process like this, and also how to set up a collaboration with a human, between a human and a robot in a kit preparation process. And that's what I had to share today. Now, if you have any questions, then we can discuss it here. Thank you very much.